In this video, we will see how to use the STM32 internal EEPROM and the advantages we have using it compared to other solutions in terms of easiness of usage, fast response, power saving, and even in terms of data protection, as being this memory inside the microcontroller chip, it is under the memory protection strategies of the microcontroller. RAM, flash, EEPROMs, and microcontrollers. Okay, a small recap of what we have already seen in other videos. When we think about the memory of a microcontroller, developing a program, handling variables, simple or complex data structures, we are usually thinking about RAM. RAM is the fastest memory technology. It is the cheapest and one of the most compact type of memory. It is used to store all the running information of a microcontroller, so it is perfect. No, RAM resets when power off, losing all the information stored. And there is information we don't want, we cannot lose powering off the system. Think for instance even just about the program we register on a microcontroller memory, programming it. We want to keep it safe powering off a microcontroller. Otherwise, we should program the STM32 anytime we turn it on. That's the reason why microcontroller is provided also with a flash memory module. That's another type of memory. It is slower than RAM, extremely slower in erasing writing information into, but keeping data when it is powered off. We have seen in other videos that there are two, let's say, types of flash memories. Two main technologies, NOR flash and NAND. Microcontroller flash memory is a NOR technology, as, broadly said here, details in other videos of my YouTube channel. That type of flash allows a faster random access, allowing microcontroller to run programs directly reading them from flash. So, program and constant data are saved on flash. And we can reset or power off the system, keeping safe the data and programs. They can restart when the system is powered back on. Other than RAM and flash, some STM32s, like the F7 and H7, have an L1 cache. That, again in few words, is a small portion of an ultra-fast RAM memory, allowing to improve performances, accessing in microcontroller programs and data. Now, in a project, other than the running data lost when the system is powered off, and the constant data defined in developing the project and stored on flash, we can have other information that could, more or less frequently, need to change, to update. And we cannot erase powering off the system. This information, that can be for instance related to the project configuration, user options, or other data to protect against power failures, can be stored in an EEPROM. EEPROM is another memory technology, usually slower than flash retrieving data, and quite faster in writings. Well, it is important for me to specify here that all I am saying about the speed of the various technologies is a generic information, let's say referred to average values of each type of memory. Single memory sets, provided by single manufacturer, can have distinctive characteristics, and we can also see that every month, maybe every week, there is a new product offering new performances. Anyway, EEPROM and flash have two important differences among others. EEPROM is designed to allow a higher number of writing cycles than flash. And EEPROM, again usually, needs a quite shorter time in the erasing writing cycles. So, avoiding to go too much into details of EEPROM and flash, I made a specific video about it, a link to it is below here in the video description. We can say that EEPROM is a technology usually specifically adopted to store small information that can change in the project lifetime, and that must be safe powering off the system. When we need this feature in a project, we have to add an external EEPROM to the microcontroller. It is usually communicating via I2C, which has the advantage to be simpler than other ports, needing just two wires. and the disadvantage to be quite slower has a minor impact, being involved in transferring small data, as I said. Anyway, the question is, as any STM32 has a flash on chip, can we use it saving data? Can we emulate an EEPROM on flash? Indeed, usually, program and constant data don't use the whole flash memory availability. Usually, in a project, we can have part of a microcontroller flash memory unused, even a large part of it. So can we use it, the free area on flash, saving our data instead of using an EEPROM added to the project? The answer is yes, that can be done. But we need to be very careful. Flash memory is specifically designed to receive, let's say, in one shot, large set of data of information to store, having it changing only occasionally. And it can be dangerous for the microcontroller flash, for the whole microcontroller chip, to use flash as it simply were an EEPROM, or, even worse, as it were a sort of RAM protected against power failures. ST provides a guideline to develop a driver emulating EEPROM flash. It is described on the EN3969 application note. Analyzing that documentation, we see that the algorithm suggested by ST is to spread the writing cycles across multiple pages of the flash memories, handling also a memory header indicating the single flash sector status and recommending to implement a garbage collection strategy in the flash handling algorithm. Again, emulating EEPROM on flash must be carefully done, and we cannot simply use one flash sector, erasing its content and writing over anytime we need to update the data stored into. So the only safe way is to use external EEPROM. If we go on the STMCU Finder, that's the module called as a first step creating a new project on CubeMX or even on CubeIDE, opening STMCU Finder, on the MCU selector, I can select the characteristic I need on a project, identifying the correct microcontroller. And here you can see I can choose the ARM core I need, types and numbers of communication ports, timers, and so on. Here I can select the quantity and the type of memory I need. And we can see that there are some STM32s having an EEPROM on board. If I filter microcontrollers excluding the ones without EEPROM, I can see that this type of memory is available on the L0 and L1 series. As we know, the L family is, let's say, an evolution of the STM32F family, mainly improved in terms of power saving. They are oriented to battery-powered projects, even if obviously we can use them also in projects connected to the main. If this is not the first video you see on my YouTube channel, you know I like to use the JLC PCB services developing my boards. And within the JLC PCB catalog, there is an L1 and an L0 STM32 in the preferred extended part list. Devices marked as preferred extended can be used as basic parts in projects requiring an economic PCB assembly. That's why these two microcontrollers are in my personal part list. So, adopting an STM32L0 or L1, we have the advantage of an easier project design, not needing an external EEPROM. Being also cheaper, taking the advantage of a GLC PCB catalog developing the board. So, let's go deeper in this device, the onboard EEPROM of the L0 and L1 series. I will use for my test a Nucleo 64 L152RE. Referring to the reference manual, analyzing the microcontroller organization and characteristics, we can see that information shown are based on a category classification. And the L152RE I'm using is a category 5 microcontroller. We will need this information next. Anyway, despite the category, we see that EEPROM is located into the flash memory area and both flash and EEPROM are controlled by the same FLITF interface, managing read, program and erase operations on the non-volatile memory, the NVM device. That's the name in ST documentation. Handling flash and EEPROM with the same interface means that when an erasing or writing operation is running over a device, for instance on EEPROM, other operation cannot be executed on the NVM until writing completes. For instance, even reading the next program instruction from flash, program that freezes. More correctly said, you see that manual refers to banks, not to the whole memory. That's because some microcontrollers of the L0 and L1 lines have flash memory and EEPROM also split into banks. As you can see, L152RE is one of these devices, and we will test this opportunity, having one bank involved in an EEPROM writing cycle, while the other one is free to execute other operations, for instance, as we said, free to proceed executing program. Erasing and writing operation timings is measured in TPROG timing steps. Datasheet shows that this time is about 3 to 4 milliseconds. Okay, after having seen the main architecture of the NVM device, let's go into EEPROM handling details. EEPROM can be written by bytes, 16-bit half words, 32-bit words, and 64-bit double words. For each data type, there is a description on the reference manual of how to perform reading and writing operations. But all of them follow the same sequence. After a microcontroller is set, NVM is in a write protected status. We can unlock writing on EEPROM, sending a PE key 1 followed by PE key 2 sequence to the flash PE key R register. EEPROM can be set back to write protected mode, setting the PE lock bit into the flash PECR register. Once writing serial load, an erasing operation on EEPROM is performed just writing 0 into the location to erase. Writing 0 to the location, FLITF starts an erasing sequence. Reference manual shows that EEPROM erase is limited to word and double words. Erasing operation stores EEPROM bank for one tprog. That's about erasing data on EEPROM. Writing operation can be performed in two ways, depending on the FTDW bit set in the PECR register. If a bit is clear, FLITF interface writes data into the destination in one tprog cycle if the location was previously cleared. The operation takes two tprog steps if the destination content is not 0. If FTDW bit is set, writing operation takes always two tprog cycles. As in this case, FLITF performs always a destination clear before writing. In order to verify the completed writing or erasing operation, we can test the busy bit on the flash status register. Other bits confirm the correct EEPROM operation or signal an error condition. A library provides function to handle EEPROM. Having function to lock, unlock the memory writings, erase and program EEPROM locations. Functions have a parameter indicating the data size involved in the operation, byte, half word, word. There are write functions and fast write ones, which clear FTDW bit before writings. Having these features, as per the microcontroller documentation, I prepared a series of tests measuring timing and results over various EEPROM operations. The same tests are repeated in 3 different projects, implementing tests in different ways, but all of them having the same CubeMX configuration I show you here now. Projects have just the default nucleo board configuration, as the device to test is internal to the microcontroller. I set the microcontroller clock to 32 MHz, the fastest speed available. I enable a timer. I will use its counter measuring time. To do that, I usually enable a basic timer like TIM7. And having a 32 MHz clock, I set a prescaler to 31. So TIM7 will count on a 1 microsecond base. That's all about CubeMX. Having saved project, opening the linker script, I defined 2 memory areas corresponding to the 2 EEPROM banks and 2 sections related to the 2 memory areas. Then I defined 2 variables, on bank 1 and on bank 2, stored on the 2 memory-defined sections. This way, the 2 variables will be stored in the 2 distinct banks. The assignment of variables in a specific memory area works this way. In the variable definition, in your program, add the attribute section. Inform the compiler in which memory section must be stored the variable. Variable on bank 1 must be in bank 1 section. On bank 2 must be in bank 2 section. Then in the linker script, I informed that bank 1 section must be in EEPROM_B1 memory area, while bank 2 section is addressed to EEPROM_B2. In the memory area definition, I specify that EEPROM_B1 starts from 808 4x0 and its size is 8K. EEPROM_B2 starts from 808 2000 with the same 8 KB size. Note that here in the linker script, memory sizes are defined in bytes. These addresses and sizes are from the reference manual we have already seen. And they can change, changing the microcontroller used. Now in main.c, before entering into the main loop, I run a test function. I will run it one time on the onBank1 variable, and one time with onBank2. Tests are repeated 3 times, changing the data size tested. Bytes, half words, words. Be aware to avoid to put this kind of test, writing EEPROMs, flash, or other heavy or destructive operations, inside the main loop, as if test goes out of control for any reason, it can quickly burn out devices, chips, and so on. Test function performs this series of operations, measuring timings and results. I try to erase a word on the locked EEPROM. I try to write into the locked EEPROM, and the EEPROM unlock. Then a series of tests in erasing the EEPROM content and writing into, using write and fast write command. An operation will be repeated on an EEPROM location containing non-zero values, an EEPROM with a zero content in a non-zero word, an EEPROM location having the full word set to 0. As I said, this test series will be repeated on bytes, half word and words, and applied to erasing, writing and fast writing command. For instance, the erase a byte test will be repeated on a byte with FF value. Being an erase command, it will be set to 0. A byte already set to 0 within a word having a non-zero value. Erase will add the byte 0 and changing the word value. A byte set to 0 within an EEPROM word fully set to 0. Also in this case the word will keep unchanged. The half word test follow the same logic applied on an half word EEPROM location. This way we will see the capabilities to handle different data sizes and the related performance. In the first version of the test, I will use the functions provided by HEL library. For each function used in the test, I just apply the corresponding HEL function. Detecting the timer 7 counter value before and after the function call, I will measure the time needed. That's the result. Values in microseconds. Lock and unlock functions are fast. Even unauthorized attempt to write or erase EEPROM return quite quickly. Times in erasing and writings execute as expected on TPROC steps of 1.6-1.7 milliseconds. So, analyzing timing on a TPROC base, we can easier note some details. Results are the same, writing either bank 1 or bank 2. I haven't assigned a specific location for the test function, but we can see that the whole program is stored on bank 1. But we don't see there are no differences in having EEPROM writings either on bank 1 or on bank 2. Same timings. Same timings also in erase, write, fast write functions. And here we see that timings are related to the value stored in the whole word in EEPROM, not just to the value of a byte half word involved. Consider these tests. I am writing 0 on a byte which is already 0, so it will be unchanged at the end of the operation, in both these two tests. But the time needed to do this operation is 2tprox if the rest of the word, which should not be involved, is not 0. If it is 0, time is 1tprog. The same is writing into a location. Timing is related to the whole word value, not just to the byte or half word involved in writing. If the whole word is 0, writing will require just 1tprog cycle. That because, as we have seen in the reference manual, FLITF erase involves a full word. So asking to erase just a byte, FLITF will perform two operations, a word erase and a write back bytes in the word not involved by erasing. So it seems clear the reason why these timings. While it is not clear why bank 1 and bank 2 need the same timings. Trying to get more information about the EEPROM busy timing, I set up a second series of tests. In the Flash HAL library file, we see that it provides a wait for last operation function. Going into it, we see that it simply loops, waiting for a busy flag clears or a timeout expires. Then it just checks the operation completed, and if there are no errors, it returns OK. So I changed the testing function. Adding a call to wait for last operation before executing writings, and measuring the two times, the waiting for a free FLITF time and the writing erasing operation time. We should see, at least on bank 2, that the program loops waiting for a free FLITF. That's the results. For each test, the first time you see is the wait for last operation time. The second time is what needed by writing erasing operation. As you see, EEPROM is always available. Wait for last operation returns in few microseconds. Moreover, again, there are no differences in bank 1 and bank 2. Half writing commands, I mean both writing and erasing commands, stall until the operation ends, returning only when FLITF is not anymore busy. OK, I need to take a look inside the half writing functions. Here we see that before starting a writing operation, HAL function correctly tests FLITF is free to proceed. Then it starts a writing function as per the specific data time to write. And if we go inside the single writing function, we see that, OK, there is a new test for a free FLITF, it starts writing. Here you see it clears the FTDW bit when the command is fast writing. But what is remarkable is that before returning, function calls again wait for last operation. That is why the HAL function stall. Even if we could proceed, HAL function loops, waiting for the confirmation for the writing complete. Regardless the writing bank is the same of the running program bank or not, HAL function loops until the writing is complete. There is no parallelism between the two banks involved. So I set up a third test. This time not using HAL and directly handling EEPROM writing and erasings. As you see, before writing, I verify that FLITF is free, and that is right. I must be sure that I can access the EEPROM before starting a writing operation. This function just loops for the busy bit clear, measuring the time needed to exit the loop, waiting for the free FLITF. Then I will clear FTDW bit if the operation to perform is a fast write operation, otherwise I set it. Finally, I simply write data into EEPROM, without a new wait for writing complete loop at the end. Finally, we have different results writing either on bank 1 or bank 2. You see that writing on bank 1, the bank storing the program, writing function takes the full TPROC time. That's not for any busy testing loop. It is due to the MVM bank 1 hanging to complete the writing operation. Even flash hangs on bank 1, and as program is on it, even reading the next instruction to run hangs. So we can read the TIN7 counter value only when FLITF ends the EEPROM writing. In the other case, writing on bank 2, after starting writings, program is free to proceed, as FLITF can complete writings on bank 2 while it is reading on bank 1. This way, we see that the writing command needs just some microseconds, and then, proceeding in the program, test function will loop waiting for the free bank 2 before start a new writing. So these are the functions I will use handling the on-chip EEPROM of my STM32L1. Consider that this function could need some slight changes to be applied to some other microcontrollers of the L0 or L1 line. Having EEPROM inside the microcontroller allows also to include it into the memory protection strategy. L0 and L1 have a set of option bytes allowing the configuration of some features of the microcontroller, like the behavior when it enters in stop mode or standby mode, the behavior of the independent watchdog, and so on. Option bytes allow also to define the reading protection of the MVM. The RDP option byte defines the level of the flash and EEPROM protection. 3 protection levels are available. In level 0, flash and EEPROM are always available. Read and write operations are available in all the boot configuration. In level 1, flash and EEPROM are fully available only if a microcontroller boots from flash. If booting from the RAM or in debug mode, MVM reading and writings are not allowed. This way, booting from flash, microcontroller can access the full memory, but we cannot read flash content and EEPROM data, accessing, for instance, microcontroller in debug mode. We still can set the option byte back to 0, and this way a mass erase will be performed on the microcontroller, allowing to reprogramming EEPROM and flash without accessing to the information previously stored into. Protection level 2 is a permanent, irreversible operation. Debug is permanently disabled. Memory is permanently protected. Other features are available having EEPROM inside the microcontroller. Just for instance, we have a faster and easier control of powering in the various low power mode of a microcontroller, improving the power consumption control in a battery power project. That's all. Keep in mind designing your project that you could have a simpler and a cheaper PCB design using L0 and L1 STM32 lines. Together with improved security and power consumption control. So, have fun with your STM32 L0 and L1, and see you on the next video. Ciao!